In the early stages of the universe, matter and energy were highly concentrated and organized. Stars formed, galaxies took shape, and intricate structures emerged. However, as time goes on, the universe moves towards a state of maximum entropy, also known as heat death. As the universe expands and galaxies drift apart, energy becomes more and more evenly distributed. Stars, which are the primary sources of energy, eventually exhaust their fuel and enter a state of cooling and dimming. With no new sources of energy being generated, the universe becomes darker and colder. In this state, even black holes, which are incredibly dense and powerful objects, will eventually evaporate due to Hawking radiation. As more and more time passes, the universe becomes a desolate and lifeless place, with only remnants of cold, dispersed matter remaining. In the final stages of heat death, the universe reaches a state of maximum entropy. At this point, no useful work can be extracted from the available energy. The temperature throughout the universe becomes uniform, and all processes that require energy cease to occur. Essentially, the universe becomes a vast, dark, and stagnant expanse. It's important to note that the timescale for heat death is incredibly long, spanning billions and billions of years. It represents a hypothetical future scenario based on our current understanding of physics. While it may seem bleak, the concept of heat death reminds us of the fleeting nature of energy and the inevitable march towards disorder. Currently, the universe's expansion, characterized by the Hubble constant, is not accelerating fast enough to disintegrate local structures like galaxies. These structures are held together by gravitational forces, which are still stronger than the expansion rate. However, if the rate of acceleration were to steadily increase to infinity, a point could be reached where the gravitational forces that hold galaxies, stars, and even atoms together become overwhelmed by the expanding dark energy. As a result, the objects in the universe would begin to stretch out and eventually disintegrate into their constituent particles. The process of the Big Rip would be catastrophic. As the universe expands, galaxies would be torn apart, stars would be ripped to shreds, and even individual atoms would be torn asunder. The expanding dark energy would overpower the strong nuclear force that holds atoms together, leading to their complete destruction. This relentless expansion would continue until the energy density, scale factor, and expansion rate become infinite, effectively culminating in a singularity that signals the end of the universe. The consequences of the Big Rip would be profound, as the universe would be left as an empty void devoid of all structure and meaning. It's worth noting that the Big Rip is still a theoretical concept, and its occurrence depends on the nature of dark energy and the precise equation of state governing its behavior. While current observations indicate that the expansion of the universe is accelerating, it remains uncertain whether this acceleration will continue indefinitely or reach a different outcome. According to the Big Crunch theory, if the gravitational force of matter within the universe is strong enough to counteract the initial explosive force of the Big Bang, the expansion of the universe would gradually slow down. As a result, the space between galaxies would begin to shrink, and eventually, galaxies would merge together. As the collapse progresses, all matter and energy in the universe would converge into a single point of infinite density and temperature. This point is often referred to as a singularity. The intense heat and pressure generated during the collapse would cause the universe to become one massive fireball, filled with radiation from stars and high-energy particles. At the final moments of the Big Crunch, the universe would reach a state of extreme density and temperature, where neither time nor space would remain. It would be a culmination of the collapse, with the universe transformed into a highly energetic state. However, the story might not end there. The Big Bounce theory suggests that instead of a complete annihilation, the universe could experience a rebound, leading to another cycle of expansion and contraction. In this scenario, the collapse of the universe would give rise to another Big Bang, initiating a new phase of cosmic expansion and the formation of a new universe. The idea of a big bounce stems from the notion that the universe is caught in a cyclic process, with each collapse and subsequent expansion setting the stage for a new cosmic epoch. While this theory remains speculative, it offers an intriguing alternative to a definitive end of the universe. The concepts of the Big Crunch and Big Bounce highlight the ongoing exploration of the nature of space, time, and the fundamental forces that govern our universe. While our current understanding and observational data point towards an accelerating expansion, the possibility of a cyclic universe opens up fascinating avenues for further scientific investigation. Imagine a scenario where the Higgs field transitions to a lower energy state, akin to rolling down into a deeper valley. This transition could occur in two ways. Firstly, an event with sufficient energy could propel the field over the energy barrier and into the lower valley. Secondly, through a process called quantum tunneling, a Higgs boson particle could spontaneously shift from one energy state to the other, creating a tiny bubble of the more favorable energy state within the field. Once this vacuum bubble of the more stable energy state is created, it would rapidly expand at the speed of light. As it grows, the bubble would engulf and annihilate everything in its path. The fundamental laws of physics and chemistry as we know them would cease to exist, and the entire fabric of the universe would be rewritten. Interactions between particles, fields, and forces would become unrecognizable. The universe we know would be torn apart, and the consequences would be catastrophic. From the macroscopic to the microscopic, the vacuum decay would dismantle galaxies, stars, planets, and even individual atoms. Eventually, the expansion of the vacuum bubble would reach a point where it engulfs the entire universe, leaving nothing but a desolate void. What makes vacuum decay particularly unnerving is the possibility that it could happen at any moment, without warning. A catastrophic event that would render everything we know and hold dear to be instantaneously obliterated. However, it is important to note that vacuum decay is currently a theoretical concept. We have no concrete evidence to suggest that it will occur. Nevertheless, the mere possibility serves as a stark reminder of the fragility and transience of our existence. The universe, with its infinite expanse and age spanning billions of years, holds a multitude of secrets that continuously challenge our scientific endeavors. Each new discovery we make only serves to uncover more questions, further pushing the frontiers of our understanding. The very existence of the universe, emerging from seemingly nothing in the Big Bang, is a remarkable phenomenon that elicits wonder and awe. How did this vast expanse of space and time come to be? What forces shaped its evolution and continue to drive its expansion? These questions fuel our curiosity and propel us on a never-ending quest for knowledge. The universe's unpredictability, reflected in the various theories of its ultimate fate, stimulates our imagination and inspires scientific exploration. We are driven to seek answers, to unravel the mysteries that surround us. It is in this pursuit that we find meaning and purpose, as we strive to comprehend the workings of the cosmos. The beauty of the unknown lies in its capacity to captivate our minds and challenge our perspectives. It is a reminder that there is always more to learn, more to discover. The universe's vastness reminds us of our own infinitesimal place within it, humbling us and igniting a sense of curiosity and wonder. In our quest to understand the universe, we develop theories and models based on the best available evidence. Yet, we remain aware that these models are subject to revision and refinement as new information emerges. The beauty of the unknown lies in the realization that our current understanding is only a fraction of the whole picture. The unknown invites us to dream, to explore the realms of possibility beyond the confines of our present knowledge. It sparks our creativity and fuels our pursuit of scientific progress. As we push the boundaries of human comprehension, we are continually rewarded with new insights and revelations that expand our understanding of the universe.